Hello everyone. In today's video, we are going to talk about work, energy, and power. Let's start with work in this video, and my following video will be for energy, and the next video will deal with the power. So let's see what is work. Let's assume there is a box lying on the ground, and if we apply a force, let's say this is the box lying on the floor, and if you apply a force, we are applying a force F. There is a displacement in the box. That means the box will move from here to here. Okay. Now this is considered as a displacement of the box. So when we apply a force on this box, and if the box moves, that means it creates a displacement, we say that work is done. So work depends on the force applied and the displacement. Next thing is that, say for example, if there is a wall, let's assume there is a wall and we are applying a force on the wall. Okay, we are applying say there is a person who's trying to push the wall. Okay, let's say this is a person, he's trying to apply force on the wall. But of course, this is a wall, this is a rigid body, it does not move. If there is no movement of the wall, that means displacement equals to zero. If displacement is zero, we say work is also equal to zero. So in order for us to do work, there has to be some displacement. If there is no displacement, then we say that the work done is zero. Similarly, if a coolie, let's assume this is a coolie. If a coolie is standing with a bag on his head, okay, a coolie is standing with a bag on his head. What will happen is after some time, this coolie will get tired and, he will have to put the bag down. But again, if the coolie is standing with a bag on his head for 1 hour, let's assume he's standing for 1 hour, we say that again, work done is equal to zero because displacement is equal to zero. The bag is not moving. So displacement equals to zero, work done is also equal to zero. Even though the coolie gets tired, we say that work done is equal to zero. Now let's try to calculate, or let's try to measure what is the work done. Now when we have to calculate work, work depends on two things. Okay. The first thing is the force applied, and the second thing is displacement. If force applied is more, work done is more. If displacement is more, work done is more. Let's try to understand this by an example. Let's assume we have two boxes. Okay, we have two boxes and we are applying force on these two boxes. Okay, so let's say this is box 1, or let's say this is box A and this is box B. We are applying a force on box A, and similarly we are applying a force on box B. Both the boxes will produce some displacement. Let's say the box is displaced over here. This is box A now. So there is a displacement. This is the amount of displacement produced over here for box A. And after pushing box B, let's assume box B moves over here. Okay, now this is the displacement for box B. So let me just write it down. This is the displacement for box A, and this is the displacement for box B. Now what we are saying is that if the displacement of both the boxes is exactly same, that means displacement of A is equal to displacement of B. Okay. Now the force applied over here, let's assume is F1, and the force applied over here is F2. Now in this case over here, the displacement is exactly same. Okay, both the boxes are displaced by exactly same amount. If F1 is greater than F2, then we say that F1 will do more work. If F2 is greater than F1, we say F2 will do more work, because the displacement produced by both of them is exactly same. Now let's take another scenario where we are going to say that the displacement produced is different. So let's go through that. Again, we'll assume the same thing. We have two boxes. Okay, so we have two boxes. Let's say this is box A and this is box B. Now, in this case, what we are going to say is that the force applied is exactly same. So now I'm going to draw the force. Let's say this is force F1 and this is force F2. And what we are saying is that F1 is equal to F2. If F1 is equal to F2. Remember, in our previous example, we assumed that the displacement was exactly same, but now we are saying that forces are exactly same. If this box A moves and it produces some displacement, okay, so the displacement produced by box A, we are going to say is SA, and the displacement produced by box B, we are going to say is SB. If SA is greater than SB, we say work done by our force F1 will be more. If SB is greater than SA, then we say work done by F2 will be more. So in short, what we are saying is if F1 is greater than F2, F1 does more work. If F2 is greater than F1, F2 does more work. And the second scenario is that if SA is greater than SB, more work is done on box A. If SB is greater than SA, more work is done on box B. So technically speaking, for the measurement of work, work is a product of force and displacement. This is a very important equation. Work is a product of force and displacement. Like we said, like we saw in our previous examples, work depends on the force applied and work also depends on the displacement produced. So from that we get an equation, work equals to force multiplied by displacement. So if work equals to force multiplied by displacement, and if displacement equals to 0, in that case we say work equals to F multiplied by 0, which is also equal to 0. So if displacement is 0, work done is also equal to 0. Now in this equation, we have assumed one thing over here is that the displacement and the direction of the force are exactly same. If you see, this is the direction of the force. going from left to right. Here, direction of the force going from left to right. And the direction of displacement, remember the displacement will also go from left to right. In this case also, the direction of displacement is exactly same. So this is one important assumption over here, that the direction of the force and the direction of the displacement is exactly same. Both are going from left to right. Now let's take a case in which the direction of the force and the direction of the displacement are different. Let's assume we have an inclined plane AC, and on that inclined plane we have a box. We are applying a force F, and the box is displaced to the top of the inclined plane C. Now the direction of the force is horizontal over here, and the direction of the displacement is in a certain angle, which is going up across the slope. So in this case, the direction of the force and the direction of the displacement are not same. So we cannot use our formula W equals to F multiplied by S, because in order to use this formula, the direction of the force and the direction of the displacement has to be exactly same. But in this case, the direction of the force and the direction of the displacement are different. So in order to find the work done, what we have to do is, the displacement is inclined at an angle theta. Now we want to find what is the horizontal component of force, the horizontal component of displacement. AB will be considered as the horizontal component of displacement, and BC is considered as the vertical component of displacement. Now remember, the force is in a horizontal direction. So we have to find what is the horizontal component of force. We don't care about the vertical component in this case. Remember, direction of force and direction of displacement will become same if we find what is the horizontal component of displacement. By using trigonometry, we can find what is the horizontal component of force. Now remember, cos theta, uh, let me just erase this part a little bit so we have enough room. Okay, so I'm going to make some space over here for my calculations. Okay, so now let's start with our trigonometry. Remember, cos theta equals to base upon hypotenuse. So in this case, we can say cos theta equals to base, which is AB upon AC. Now remember, AC, which is this part over here, the inclined surface is our displacement. So we can say cos theta equals to S upon, oh, sorry, base upon hypotenuse. So it will become AB upon S. So now we can find what is equal to AB. AB equals to, this S will multiply with this cos theta over here. So AB equals to S cos theta. Now remember, AB is the horizontal component of our displacement. So instead of F, we can use the horizontal component, sorry, instead of S, we can use the horizontal component of S. So from our formula, F W equals to F into S. Now remember, displacement was not same. So we found what is the horizontal component of displacement, which is S cos theta. So now substituting the value of S, we get W equals to F multiplied by S multiplied by cos theta. So we have our second formula. If the direction of the force and the direction of the displacement is not same, work done equals to F into S into cos theta. We have found what is the horizontal component of displacement. In second method, what we are going to do is we are going to find we are going to find the components of force. Okay, so let's start with the second part, how to derive the formula. Okay, now we have the same situation over here where there is a box on an inclined plane, and we are going to find what is the formula for work done when the direction of the force and the direction of the displacement are not same. Now remember, in the first example, what we did was we found the horizontal component of displacement. So if the direction of force was this, sorry, if the direction of force was horizontal, the force was in a horizontal direction, we found what is the displacement also in the horizontal direction. Okay, so this is the direction of the force and this is the direction of the displacement, which came out as S cos theta. Now, in this second part, what we are going to do is we are going to find what is the inclined component of force. Now, remember, displacement is in this direction, S, and force is in this direction, F. Now, we are going to find this inclined direction of force. What will be the value of this force if it is at a certain inclination? So then the component of force and the direction of the displacement, both of them will be in the same direction. And we can find what is the work done in that case. So let's try to do that. Now in that case, what we are going to do is, this is our force, AD is our force, and we are going to extend the line AE, which is in the direction of the displacement. So direction of AE and the direction of the displacement is exactly same. So we have to find what is the component of force, AE. We have to find what is AE. Again, if this angle is theta, this angle will also be equal to theta. So use our same formula, cos theta equals to base upon hypotenuse. So cos theta equals to base, which is AE, upon hypotenuse, which is AD. Now remember, AD is our force, F. So we can say cos theta equals to AE upon force F. So cos theta equals to AE upon force F. Now we have to find what is AE, which is the inclined component of force. So from this we can say AE equals to F cos theta. So we have the inclined component of force, which is F cos theta. So looking at our previous formula, work, work equals to F into S. Now we found what is the inclined component of force, which is equal to F cos theta. So instead of F, we can replace it by F cos theta. So work equals to F into, F cos theta multiplied by S, which is the same thing as W equals to F into S into cos theta. So we can find the formula for work by finding the component of force or by finding the component of displacement. In both the cases, the formula is exactly same, which is work equals to F into S cos theta, where theta is the angle by which the surface is inclined, theta. Now, let's look at some special cases in which we are going to assume that in first case, we'll say that theta equals to 0. Second case, we are going to say is theta equals to 90 degrees. In the third case, we're going to assume that theta equals to 180 degrees. I'll explain you everything. We all will understand what this means. Okay. So let's start with the first one where we are going to say theta equals to 0 degrees. So let's start with that. First case, theta equals to 0 degrees. That means if you have a box lying on the floor and if you apply a force on the box, okay, we are going to apply a force on the box. So this is our force F applied on the box and the box is displaced. Sorry. Let's say the box is displaced over here and this is the direction of the displacement and this is the displacement basically, right? This is our displacement. Now, if you think about it, the direction of the force and the direction of the displacement are exactly same. So in that case, the angle between the force and the angle between the displacement is equal to 0. So we say that theta equals to 0. Now applying our formula, work equals to F into S into cos theta. So in this scenario, work done equals to F into S into cos 0 degree. Now we all know the value of cos 0 equals to 1. So work equals to F into S multiplied by 1, which is equal to F into S. So if the direction of the displacement and the direction of the force are exactly same, we say that theta equals to 0. And if theta equals to 0, work done equals to F into S. Now let's look at the second scenario where we are going to say theta equals to 90 degrees. When we say theta equals to 90 degrees, so this is our case 2 where we are going to say theta equals to 90 degrees. Let's assume you have a stone which is tied to a rope and the stone is moving in a circular path like this. You are rotating the stone. Now remember the direction of the stone is always, the stone is trying to go straight. So this is the direction of the displacement. The stone wants to go straight. And this is the direction, remember centripetal force. This is the direction of the force. So we can say this is our centripetal force. Now the angle between the direction of the displacement and the direction of the force is 90 degrees. So we say that theta equals to 90 degrees. So when a body is moving in a circular path, theta equals to 90 degrees. Using our formula, work equals to F into S into cos theta. So work equals to F into S into cos 90. And we all know cos 90 equals to 0. So work equals to F into S multiplied by 0, which is equal to 0. So if theta is equal to 90 degrees, work done is equal to 0. If a body is moving in a circular path, theta is equal to 90 degrees and the work done is equal to 0. Now let's look at the third case where we are going to say that theta equals to, oh, I'm running out of space over here, so I'm going to write it down over here. Third case, we are going to say theta equals to 180 degrees. Okay, so let's take our same example, what we did earlier. We have a box lying on the ground. We are applying a force and there is a displacement of the box. The box moves from this position, one position to another position. So this is the displacement of the box. And this is the direction of the displacement going from left to right. So this is the direction. Now, if you think about it, when the box is moving from left to right, the force of friction is moving from right to left. So we can say friction is moving in the opposite direction. This is our force of friction. So now if you see the direction of the force, this is the direction of the force. And let's see what is the direction of the displacement. Remember, displacement is going in the opposite direction. Now the angle between the direction and the direction of the force and the direction of the displacement, the angle between them is equal to 180 degrees. So let's try to find what is the work done when theta equals to 180 degrees. Work equals to F into S into cos theta, which is equal to F into S into cos 180 degrees. Cos 180 degree equals to minus 1. So work equals to F into S into minus 1. So we get work equals to minus F into S. This is the work done if the direction of the displacement and the direction of the force are opposite. In that case, we say that work done will be equal to negative. Now in the next part, I'm going to show you some examples which will explain us what is the work done when theta equals to 0, 90 and 180. Okay, let's start with example 1. Let's suppose an example of freely falling body. Okay, let's say for example, we have a ball which is at a certain height, h. Okay, let's say this is the ground level and ball is thrown vertically downwards and the ball was at a certain height, h. The mass of the ball is equal to m and g stands for gravity, which we will take it as 9.8 meters per second square. Now let's try to find what is the work done by this ball from moving up from this height to the ground level. Now remember our formula work. Now first of all, let's see what is the direction of the force and what is the direction of the displacement. Remember, gravity is acting vertically downwards. So this is the direction of the force and this is the direction of the displacement. The ball is going from a height to the ground level. So the direction of the force and the direction of the displacement are same. So we say theta equals to 0. In that case, work equals to F into S. Now let's try to find what is force. Remember from our Newton's, from our previous, from our 8th and 9th standard, we have studied from Newton's law that force equals to mass into acceleration. In this case, the acceleration is gravity. So we say force equals to m into g. The second important thing is that in this case, when the body is moving vertically downwards, our displacement is equal to our height. Now remember, starting point and ending point. So displacement equals to height. So looking at our formula, W equals to, instead of F, we can substitute it by m into g. And instead of displacement S, we can substitute H. So we say that work done equals to m into g into h for a free falling body. When a body is falling freely downwards, work equals to m into g into h. Now let's look at another example. Suppose a coolie, let's say this is a coolie, and there is a bag over here. Now, assume that the coolie is lifting the bag and he's going to put the bag on his head. Okay, the coolie is going to move the bag on his head. So if you think about it, this is the displacement of the bag moving vertically upwards. So this is the displacement of the bag. Now, when the coolie is applying force by his hands, remember his hands are pushing the bag upwards. So we can say that the direction of the force is also moving upwards. So in this case, the direction of the force applied by his hands and the direction of the displacement is exactly same. So we say theta equals to 0 degrees. So in that case, work equals to F into S. In the same example, this is the work done by the coolie, F into S. In the same example, if you think about it, gravity is acting vertically downwards. Remember, the gravity is pulling the bag downwards. This is the force of gravity which is pulling the bag downwards. So if you want to find what is the work done against gravity, the direction of the force is acting vertically downwards and the direction of the displacement is vertically upwards. So theta equals to 180 degrees. So in that case, work equals to F into S into cos 180 degrees, where we say work equals to minus F into S. So let's try to understand this part. The work done by the coolie, which is by his hands, is equal to F into S because the direction of the force and the direction of the displacement are exactly same. But work done against gravity is equal to minus F into S because the direction of the displacement and the direction of the gravity, force of gravity, are opposite, which is 180 degrees. Now let's look at the third example where we said that, oh, I think we have already done that. When a body is moving in a circular motion, theta equals to 90 degrees. Remember, when a body is moving in a circular motion, theta equals to 90 degrees. So work equals to 0. Okay, let's look at the one more. I think this is the last example. Let's assume that we have a coolie and he has a bag on his head. If the coolie is standing with the bag on his head for half an hour, work done equals to 0 because displacement equals to 0. Now let's say the coolie starts moving in this direction. When the coolie starts moving in this direction, that means there is displacement. The bag will move from this position, initial position, to this position over here with the coolie under it, of course. So let me just draw the coolie over here. This is the coolie. Okay, and this is our displacement. So now the coolie is doing some work. Now, what is the direction of the force? Remember, coolie is moving in this direction and friction is moving in the opposite direction, or the coolie is pushing the ground backwards. So the direction of the force is opposite. Okay, the coolie is pushing the ground backwards and the displacement of the bag is in the forward direction. So in that case, theta equals to 180 degrees. So work equals to F into S into cos 180 degrees. And remember, cos 180 degree equals to minus 1. So work done equals to minus F into S. Now remember, the direction of the force and the direction of the displacement are opposite. So the angle between them is equal to 180 degrees. Now in all the above cases, what we have assumed is that the force is always constant. That means the force never changes. So if you are applying 5 Newton force, it always remains 5 Newtons. But now let's look at a scenario where we are going to say that the force is not constant, but the force is variable. In that case, if you want to find what is the work done, what we do is we plot a graph. Okay, we are going to plot a graph with displacement and force. So we'll take displacement and force. Now displacement is taken on the x-axis and force is taken on the y-axis. If the force is variable, we'll get a graph like this, an inclined line. The force will keep on changing. Just as let's try to think about it. Force is 1 Newton, 2 Newton, 3 Newton, 4 Newton, 5 Newton. So the force will keep on changing as the displacement also keeps on changing. So in this case, we say that the force is variable. In order to find what is the work done by a variable force, what we do is we find what is the area of the graph. So this will become our triangle. Let me label this triangle. Let's say this is our origin, this is point A, and this is point B. So OAB is the area under the graph. And to find the area under the graph, that means we have to find what is this area under the graph. Sorry. We have to find what is the area under the graph. Now remember, AOB is a triangle. So the area of a triangle equals to half into base into height, which will become half multiplied by base, which is the displacement, and height, which is our force, F. So in that case, we say work equals to half F into S. So work done by a variable force equals to half into F into S. Same thing applies if we can do the same thing for a constant force also. If the force is constant, the graph will look somewhat like this. Let's say this is our force and this is our displacement. So this is our displacement and this is our force. Displacement is taken on x-axis and force is taken on the y-axis. If the force is constant, the graph will look somewhat like this, which means the force is constant. Let's say, for example, 5 newtons. The force is constant, 5 newtons, and the displacement keeps on increasing. Again, same formula applies over here. We can find what is the area under the graph. This is the area under the graph. And it looks like, this area is a rectangle. Now we all know how to find what is the area of a rectangle. L into B. Okay. So area of a rectangle equals to L into B. Let's say this is our length L and this is our breadth B. So L equals to S and breadth equals to F. So again, work done equals to F into S. Now you can do the derivation by a graph, or you can do it mathematically, which we have done earlier. In both the cases, work done equals to F into S if the force always remains constant. Okay, so last thing what we want to figure out is what is the unit of force. Okay, let's try to figure out what is the unit of force. Remember, sorry, unit of work, my bad. Work equals to force multiplied by displacement. So what is the SI unit of force? It is Newton. And what is the SI unit of displacement? It is meters. So the unit of work equals to Newton into meter, which we call it as joule. So joule is the SI unit of work. Now let's try to figure out what is 1 joule. In order to define 1 joule, we put 1 in front of joule, we put 1 in front of the Newton, and we put 1 in front of meter. So basically it means that when a force of 1 Newton is applied, 1 Newton force is applied, and it produces a displacement of 1 meter. Displacement equals to 1 meter. Then we say that work done equals to 1 joule. The bigger unit of work is kilojoules. Kilo means 10 to the power 3. So 1 kilojoule equals to 10 to the power 3 joules, which is basically 1000 joules. Second bigger unit is megajoules. Mega means 10 to the power 6 joules. We can also have a gigajoule, which will be 10 to the power 9 joules. Now, what are the smaller units of force? This is the bigger unit of force, what we have studied. Now, let's try to figure out what is the smaller unit of force. One small unit of force is 1 millijoule. Small m and joule. That means 10 to the power minus 3 joules. And then we can also have 1 microjoule, which will be equal to 10 to the power minus 6 joules. So these are the units of work. Now let's try to figure out what is the CGS unit of work. Same way, work equals to F multiplied by S. So what is the CGS unit of force? It is dyne. And time displacement is centimeter. So dyne multiplied by centimeter, which we call it as urge. So urge is the CGS unit of force, ERG. Okay, we already know 1 Newton equals to 10 to the power 5 dyne. This is the SI unit of force, and this is the CGS unit of force. Now let's try to figure out what is the relationship between the SI unit of work and CGS unit of work. Now the SI unit of work is joule, so let's say 1 joule. Now remember, 1 joule equals to 1 Newton multiplied by 1 meter. Now, what is 1 Newton? We already have written over here 10 to the power 5 dyne. So 1 Newton equals to 10 to the power 5 dyne. And what is 1 meter? 1 meter is equal to 100 centimeter, or we can say 10 to the power 2 centimeter. So this will be 10 to the power 2 centimeter. So altogether we can say 1 joule equals to 10 to the power 7 dyne centimeter. And we know dyne centimeter is equals to urge. So 1 joule equals to 10 to the power 7 urge. This is the relationship between the CGS and SI unit of work. This is all about work. In the next video, we'll talk about energy. I know this was a long video, but just go through it. The next video will be a little bit shorter one. Thank you for watching, and please comment whatever you have to say about this video. Thank you.